let's try to see the integration points. This is very important concept in FEA, and one should or must know about integration points. Based on this, in next chapter, we will be able to easily understand the R glassing and shear logging and volumetric logging concepts. Okay. So let's see integration points. These are also called Gauss points. Basically, in previous lecture, we have seen that uh, to perform or to obtain the element stiffness matrix for any element, we need to perform a double integrals. Okay, this is for 2D case. For 3D case, it is a triple integration. Okay. And this is in natural coordinate system. Now, what happens when we talk about computers and programming? In computers or any programming language, we can do integration, okay, or summation. We can do both, but let's talk about a simple domain. Okay? Simple domain, and if we do a simple integration, and if we do a summation, the integration is 10x to 1000x slower compared to summation. And this is we are talking about very simple integration. Okay. It is such a slower that we can imagine when we are talking about double integration, it will be even more slower, and triple integration, it is even more slower. And remember, this is only about one term. In FEA, we have for one element, for example, uh, linear quadrilateral element, we have 8 by 8 matrix. Okay. And in this matrix, all 64 terms, okay, have double integrals. So we need to perform 64 times double integrals to obtain stiffness matrix for one single element. Now there could be a million and 10 million elements in FEA. In real industrial case, it is 1 million and 10 million are very common. So imagine that when we perform uh, integral, double integrals of this level model, how slow the computations are. Okay. And we are talking only about double. Triple integrations, the speed is even more slower. So in order to get rid of such issues, okay, there is a Gauss quadrature rule. So what Gauss quadrature rule does, it we can basically move from integrals to integral over element domain, okay, to a summation at the discrete points. So basically it is integral or integration to numerical integration. Similarly, we can say double integration to double numerical integration or double summation. So we can imagine the summation is very straightforward even in computers. In integration, we need to find the limit, and there are very no for one term it is easy, but uh, in general the computation is very is not that straightforward. Okay, it is unlike in summation, it's just very simple. So Gauss quadrature, with the help of Gauss quadrature, we can improve the performance, okay, or speed of the FEA calculations. So we should thank to Gauss quadrature. Okay. If Gauss quadrature wouldn't have been there, okay, the analysis which is taking 1 hour time for example, could have taken 1,000 hours or 100 hours depending on complexity of problem. So that's why we use Gauss quadrature. Now let's talk about Gauss quadrature. After understanding the purpose of Gauss quadrature, so we have this element stiffness matrix, and this is our 8 by 8 terms, okay, 64 matrix terms. So we need to perform double integration over this 8 by 8 terms. And what exactly Gauss quadrature does is it will we will be convert this into double summation, okay, over 8 by 8 terms. So let's say Gauss quadrature for 1D or single integration. So if we have some function of x and we want to do integration from -1 to 1 limit, okay, the Gauss quadrature rule, it states that we can do a summation, okay, from uh, summation at I equal to 1 to n number of points, okay. These are called Gauss points or integration points, and we can replace this integration with summation at discrete points. So this becomes f of xi, and with weighting factor multiplication. So this is for 1D. Now let's apply this to our stiffness matrix. So K element stiffness matrix is, let's take eta equal to -1 to 1 here, and we will consider first this term. Okay. So this is zeta equal to -1 to 1, 8 by 8 matrix terms, e zeta and d eta. So this is 1D. So we'll apply this rule onto this term. So we get eta equal to -1 to 1. This will be replaced by summation. So I'll have summation over I equal to 1 to n with the weighting factors and d eta. So this is a function of eta I, zeta I. Now this is one term, and let's take this term and we can do a again apply the same Gauss quadrature rule on this 1D case. Okay, so this is our function. This complete is one function. So we can further apply summation. So now this term I equal to 1 to n. This is for zeta, which is 8 by 8 matrix terms wi. Now for this we'll again apply another summation on the top of this numerical integration. So this now is equal to I equal to 1 to n. We are taking same number of integration points for zeta and eta, and again another weighting factor for eta. So this is for zeta and this is for eta. So this is what we get, okay, from double integrals to double summation, okay, and these terms are function of zeta I eta I. This was zeta and eta. Now this is getting converted into uh, discrete points zeta I, eta I. Now we will come back to this K matrix. Before that, let's try to understand this number of integration points I equal to 1 to n and I equal to 1 to n. So the number of integration points n should be greater than or equal to p plus 1 by 2, where p is polynomial order, okay, of the function. So this function, what is the order of polynomial, whether zeta uh, or zeta square or zeta eta, eta square, what is that? So that is the polynomial order p. So the if we take polynomial order of 1, 1 plus 1 by 2, we need one integration point for exact uh, integration of given function. So that is the condition or requirement. And the discrete or cost points or integration points location is 0, 0. Okay. And weighting factors are 2 and 2. If we have two polynomial order, okay, number of integration points are 2 plus 1 by 2, so it is basically number of points are integer, so this is 2, okay. And so these are 2 points in each direction, okay. So if we have zeta and eta, 2 points in zeta and 2 points in eta direction, so 2 into 2 is equal to 4 integration points, and the location will be something like this. So as per Gauss quadrature rule, these 4 points have coordinates of 1 plus or minus 1 by root 3 plus or minus. So these are four combinations of coordinates, okay, of zeta I, eta I, and weighting factors are 1, 1 for all the integration, all four integration points. Okay, so with this, let's try to understand the integration points and polynomial order for first order quadrilateral element. So this is our stiffness matrix as we know, and the B matrix as we know, it is the B matrix is basically derivatives of shape functions. Okay, this is a derivative. So beta B has the terms which are derivatives of shape functions. Okay. So we know the shape functions of first order quadrilateral element. Okay, and when we try to get the derivatives of this, for example, this will have no, if we take dou n1 by dou zeta, we'll have eta after derivative. Okay, dou n2 by dou zeta will similarly have eta terms, okay, because this will become 1, this will remain same because we are taking partial derivative. So let me write here, if we take dou n1 by dou zeta, okay, we get 1 minus eta by 4. Okay. Similarly, when we take dou n1 by dou eta, we'll get minus 1 minus zeta by 4. Okay. So what I'm trying to say, when we take derivatives of shape functions, okay, they will have eta and zeta. Okay. So will this B will have zeta and eta. Maximum polynomial order is zeta or eta. Similarly, B transpose will also have zeta and eta. And D do not have no zeta eta terms. They are, that is a sigma epsilon relationship. But when we multiply this matrices, okay, the polynomial order will be of zeta, eta, zeta square, eta square, zeta, eta. So this after multiplication of matrices, the this could be the terms. So maximum polynomial order is 2. So P is equal to 2 for our first order quadrilateral element. And as per this, okay, P equal to 2, we need, this is, let me write it, number of integration points. Okay, so 2. So that means we need 2 by 2 in zeta and eta direction. So there are total 4 number of integration points. So I can further write K matrix. Okay, let's no, write at a top level. So we'll not write all the terms T and J, Jacobian matrix, determinant, all these things. So we want to just understand the big idea or top level idea. So I'll just put minus 1 to 1, minus 1 to 1. This is 8 by 8 and d zeta d eta. So this integration, as we know, will go into each term of this matrix, and we have double integrals for, that is for 64 terms. Okay. And this is the double integration. So we'll convert this into, or we can write after applying Gauss quadrature. We can write stiffness matrix as this double integration will be replaced by numerical integration summation I equal to 1 to 2, because we have two integration points in one direction, zeta and eta direction each. So total 4 integration points. And this term, whichever whatever it is, okay, this term basically is after multiplying B transpose D and B. So this term, okay, which is function of zeta eta. Okay, the maximum polynomial order is 2. So this function and weighting factors wi, wi, okay, and this will be uh, 8 by 8 matrix. Okay. So this is not exactly like this, but this is a kind of terms, or no, kind of double summation each term will have. Okay. So let's further expand this. Okay, how this for each term looks like. Okay, so I will take only one term here, and we will see for only for this one term, and other terms, remaining 63 terms can be well understood. So I will just show the top level idea for each term. So we can write this more specifically, okay, as this is a function of zeta eta. So zeta I eta I after Gauss quadrature, and wi wi. So this is our 4 integration points. So I will just write it for each term. So f of zeta I eta I. So 4 integration points. So this is 1, 2, 3, and 4. So first integration points. Okay, this is IP1. The coordinates of that is minus 1 by root 3, minus 1 by root 3. This one. And as we know, the weighting factors for all the integration points are 1 1. So we can say into 1 into 1 plus integration point to this one, okay, which is f of 1 by root 3 minus 1 by root 3. Weighting factors 1 plus this is integration point 3, okay, which has plus 1 by root 3 plus 1 by root 3, and integration point 4 minus 1 by root 3 plus 1 by root 3, and weighting factors of 1 1. So this is for only one term in stiffness matrix, okay, this one. uh, so now I can write stiffness matrix, okay, this one, okay. So I would say contribution from integration point 1 plus 2 plus integration point 3 plus integration point 4. So this is for one term. Similarly, it will be having 8 by 8 terms. What I am trying to say here, the stiffness matrix basically comes from all the integration points. Okay? So in other words, we can say that the stiffness matrix can be calculated at each integration point. Then to get the element stiffness matrix, we can submit all the components. Okay. So with this understanding, now let's you know, try to uh, understand the FEA steps which we earlier discussed. Now let's refine it more. So FEA steps. FEA steps after understanding the integration points. So as we know, the first step in FEA, so calculate the element stiffness matrix for each element in the assembly. Then we perform assembly of all the elements and we get the total or global stiffness matrix. Okay. So perform assembly of elements and we get a global system of equations. The third step is we apply loads and boundary conditions. Then solve for unknown displacements. Next step is derive other quantities like compute strains from the displacements. Then from strains we can compute stresses. These are our steps. Now let's talk about the first step, which is ke for each element, as we have seen a few minutes ago. Okay, the k matrix is coming from all the integration points. In this case, it is four integration points. First order quadrilateral element. So stiffness matrix is calculated at each integration points, and then they are simply uh, do summed up. Okay, so we can say that stresses and strains are calculated at integration points. And you would have seen, if you have done any workshop or done any project in FEA software, you would have seen the stresses and strains are basically integration point quantities, unlike the displacements. Okay, displacements are nodal quantities. So how these stresses and strains are calculated at integration? We know the stiffness matrix is coming from all the integration points, right? So now the let's talk about strains. Okay, the strains, as we know, for 2D case is B matrix and displacement factor. And the B matrix, as we know, is a derivative of shape functions with respect to zeta eta. Okay, so this matrix, in this case, it is 3 by 8 for this element, first order quadrilateral element. So it has 3 by 8 terms, and they have all zeta and eta terms. Okay, not all, some have zeta, some have eta. Okay, some have either 0 or 1, but let's take it they have zeta eta terms. So how strains are calculated at integration point? So we need to they compute strain components at all the integration points. So IP1, then IP2. Okay, it is computed just by putting the zeta eta. Okay, we know the zeta eta coordinates of all integration points. Okay, plus or minus 1 by root 3. Okay, that is our coordinates. So in B matrix we can put for IP1 whatever zeta. Okay, 1 eta 1, similarly zeta 2 eta 2. So we can put all these coordinates in B matrix, and we can find the strain components for that integration points. So this is how the strains are calculated at integration points. So this is very important to remember. Okay, and these are accurate values. Okay? These, because these are coming from direct uh, computation. So these are accurate. But in FEA software or in post processing, you would have seen that the generally when you probe the stresses and strains, they you generally probe at nodes. So they are not from the computation. I mean, not direct computation. They are actually extrapolated values from integration points to nodes. So the stresses and strains are calculated at integration points, and then they are extrapolated to nodes. So we will see this how this extrapolation and everything in detail in chapter 4 when we are talking about mesh convergence. So these stresses and strains are extrapolated here. But remember, these are integration point quantities, stresses and strains, whereas displacements are nodal quantities. So once we have epsilon ij at all integration points, then we can compute sigma ij, okay, at all integration points. So we know sigma ij is D matrix. Okay, I cannot write matrix. It should be simply D because this is tensorial notation. So D and epsilon ij. So D is just simply for 2D case. Okay? It has nothing to do with x, y, or zeta, eta coordinates. Okay? So once we have epsilon ij from all the integration points, yeah, once we calculate, we can simply calculate uh, sigma ij for all those integration points. So hope this workflow is clear. Okay, so we have seen FEA steps and kept refining no, FEA steps after understanding each concept. So this is a very much this workflow is very much important because here we are talking about integration points, and that's what we will see in FEA software.